and soil structure. Okay, the slide looks zero here. Okay, the next soil resistivity. Anybody know the formula for soil resistivity? The formula is rho and the unit is ohm meter. Okay, non-homogeneous ground. That means your rho or your ohm meter is changing as you go deeper into the soil. Okay, so this is non-homogeneous. At each layer and at each location, the rho is changing. So we have non-homogeneous. If you consider the earth or the ground homogeneous, that means they have same rho. The rho or the soil resistivity is dependent on many factors. Where you are, the soil type and the nature of the soil, the concentration and composition of dissolved substance inside the soil, the temperature of the soil, the moisture content, the water content, and the ion concentration. Also, the ion concentration related to the salts dissolved inside the moisture. Meaning to say, if you want to reduce the soil resistivity of a soil, you can put salts and then it will reduce. Basically, soil is not a conductor. The silica is not conductor, but because there is a grain and the spacing between the grains of the soil, and especially if it's wet, a current can flow through it. So the smaller the grain size, the better. But the bigger the grain size, like stone, then the current cannot flow. So you have bigger resistivity. So this is the concept of resistance. The resistance of a soil or an electrode is resistant to ground of an electrode system. It's actually the resistance between the electrode system and another infinitely large electrode in the grounding at infinite spacing. You understand? Okay, maybe because I mute, you cannot answer. But we're going to look at this concept of infinitely large electrode in the ground at infinite spacing. Just remember, we're going to do this infinitely large electrode at infinite spacing, and the electrode that you bury and infinite large. So remember these two terms later on. The soil resistivity determines factor in evaluating the ground resistance. One of the formula, one of the factor in the formula is actually soil resistivity. Very important. Directly proportional. The soil depends on the type of soil already mentioned, moisture content, and dissolved salts in the previous slide. And the grain size also influencing. The smaller the better, the temperature as well as pressure. Homogeneity is also important because if it's not homogeneous, then your rho will change. In most cases, there are several layers of different soil, and if you want to correctly model the ground resistance, you need to consider not homogeneity, but multi-layered soil. So for non-homogeneous soil, usually we can make an equivalent homogeneous soil. So you do some calculation. We have equivalent homogeneous soil representation of the soil, of non-homogeneous soil. The moisture content of the soil reduces its resistivity, as you know. The bigger the moisture, the smaller the resistivity of the soil. And the water also, same. But if your water depends on the season, the bigger the water level, the smaller the resistivity, so it's good, it's better. And also the temperature, and apparently here, the bigger the temperature, the soil resistivity increases as the temperature is decreased. That means the colder the soil is, the higher the resistivity. Now these are the typical soil resistivity for various types of soil.
Yeah.
R is rho L over A, right? Rho is, if you have a conductor or any piece, this is the length, this is the diameter, and this is resistivity of the material. So resistance for the current through that conductor or that resistor is depend on this area, and area is pi a square, right? Pi r square, which is pi distance diameter over 2 square. So L is the length, and A is area, and rho. So R is that formula, and it can be proven for hemisphere electrode. Okay, if you have a soil with hemisphere electrode, so this is 2D drawing. The radius is A, and the soil. So this is a conductor like this, hemisphere conductor, and you bury inside the soil, and the soil having resistivity rho. So rho here is actually referring to the soil resistivity. And the formula, if you connect this to your down conductor, so R as seen by the down conductor is actually rho, which is the soil rho, over 2 pi is a formula, and A is the radius of the resistivity. And as you can see, the soil is massive. I mean, this is rho of the whole soil, assuming it's uniform. So from this simple structure, R here for this hemisphere is actually the formula is rho over 2 pi A, and A is the radius of the hemisphere. Okay, as you can see here, the amount of salt improve the soil resistivity. So again, we are talking here about this is our electrode just now. Sorry, our hemisphere. The soil resistivity. So the soil resistivity change as you change with the salt content, copper sulfate, for example, inside the soil. Sulfuric acid, and so on. Okay, so if the soil is having these ions, then it can reduce the soil resistance. Now, the formula is there, and this is called resistance. Okay, resistance of the current, resistance of the current seen into the soil, into the electrode, into the soil. But if you, let's say our hemisphere again, our hemisphere electrode, then the current will flow like this. This is A, and the current will flow like this. So what it sees, this way is R, resistance, and that resistance is actually depend on R, rho. Sorry, depend on rho. So you can say this is equivalent to resistance. Resistance here, R, seen by the current. Okay, now because the frequency of the current, of course, can influence how the current flow. You can see that as you increase the frequency, the equivalent resistance cannot be simulated by just a R, but you also have a C as well as a L in series. Okay, so the equivalent circuit for the electrode actually under high frequency, not just R, but also parallel C as well as series L. Okay, so for R, if this is the case, is given by this formula, as you can see here. But for C, is given by this formula. Now, epsilon R here is actually the constant. It should be epsilon naught. Okay, epsilon naught, constant. And L here is the length of conductor. And D is diameter of conductor. For L, it has this formula. Okay, L has this formula for L, capital L. And D is the diameter. If C and L resonate at certain frequency, then you also have R like that, equivalently. Under DC current, of course, L and C is disappearing, so you just have R. So V equals to I times R. If you want to calculate the voltage, or R, that means just pure R, the high frequency. But once you go to impulse, then L and C can be significant. So you need to consider also L and C component rather than just R. But for short circuit, still people just use DC part of the resistance or impedance, if you like. Now,